So this is a first lecture out of chapter 5 over stereochemistry. And so this is traditionally one of the hardest chapters for students. It's a difficult concept until you wrap your mind around it. Once you wrap your mind around the concept, then it all becomes actually pretty easy. But this is a very visual subject. And so it really helps if you can see molecules in your mind's eye, and if you can rotate molecules in your head and things like that. But it is a difficult subject for a lot of students, a lot of definitions, a lot of terminology to understand in this chapter. So definitely a chapter to spend some time studying and make sure you understand these concepts. Okay, so we've talked about stereoisomers before. So stereoisomers are molecules that have the same constitution, meaning atoms are attached in the same order, but they differ spatially in how atoms are arranged. So we've seen examples before. So for example, between these two molecules, we looked at those as examples. They have the same constitution. It's a chlorine, carbon, carbon, chlorine in both molecules, but the atoms are arranged different spatially. So one's a cis isomer, right? This is the cis isomer, and this is the trans isomer. And we've also seen these examples on rings. If you have two things attached to a ring, they could both be attached to the same side, so both on top or both on bottom, so that would be cis. Or one could be on top and one could be on bottom, and that would be trans. So again, those are all just spatial isomers, and these type of, so they're stereoisomers since they're spatial isomers, and these type of stereoisomers are called geometric isomers. So geometric isomers is just one subcategory of stereoisomers. So in this chapter, we look at other types of stereoisomers called enantiomers, diastereomers, and mesocompounds. And so technically, geometric isomers are a subcategory of diastereomers. And so I'll lay it all out for you later. But we'll look at other type of diastereomers in this chapter, along with enantiomers and mesocompounds. Okay, so where it all begins is with this concept of chiral centers. So an atom with 4 different things attached to it has what's called a stereogenic center, or a chiral center. So an example would be this molecule, carbon with the fluorine, chlorine, bromine, and iodine attached. So that carbon has 4 different things attached. So that is a stereogenic center, or a chiral center, or a chiral carbon. All the same thing. So chiral and stereogenic basically mean the same thing. Okay, so these 4 groups on carbon can be arranged spatially different. So if these models, hopefully these models are easy for you to see. So you have a carbon with a green, a red, a white, and a blue atom attached. And if I take, let's see, so 2 molecules, they both have a green, a red, a white, and a blue atom attached. And if I take these 2 molecules, if I line up the green and the red, so if I line up the green and the red, then the blue and the white don't match. So if I line up the blue and the white, then the green and the red don't match. So it doesn't matter what you line up. If I line up the blue and the red, then the green and the white don't match. So it doesn't matter what you do. You can take these 2 molecules, you can rotate them in space however you want to, and you will never be able to superimpose them on each other. And the reason why is simple, is because they are different molecules. So they differ in the spatial arrangement of 4 different things around a chiral center. And so those are another type of stereoisomer. So if I bring a 3rd molecule in, and so it's got the same 4 atoms attached, blue, white, red, and green. So I have 1 chiral center, I can only have 2 different stereoisomers. So of these 3 molecules, 2 of them must be the same. So let's see, are these 2 the same? So if I just make 2 of these match, at least 2, then in this case you can see that all 4 of them match. The blues match, the reds match, the greens match, and the whites match. So if I grab the 3rd molecule, then this 3rd molecule is different than these 2 because these 2 are the same. So if I just get rid of 1, no magic trick, right? I just dropped 1. And so you can see now that if I line up two of the atoms, the other two are not going to match because it's a different molecule. So a molecule with one chiral center can have at maximum two different stereoisomers, right? So we could depict that like this, for example. So we have a chlorine attached to a carbon, which is attached to a bromine. And then what else we got? A fluorine and an iodine. And so if I wanted to draw the other molecule, then I can simply draw a mirror image of it. So if we let this reflect across the mirror, then a chlorine here down to a carbon, and then the bromine this way, and fluorine there, and iodine there. So if you took one of these models, and if you just wanted to play with this yourself, so let's just say the chlorine is green, and so from my perspective, I don't know how it looks on the camera from your perspective, if it's reversed or not. So this would be bromine is in red, and then this is going away from me, so that would be fluorine, we'll call that white, and this would be coming towards me, so the blue atom is coming towards me, so we would call that blue. And so if I find the enantiomer, let's see, is this the same or is this the enantiomer? That one's the same. So all four of those match, so I grab the other one. So this one should be then the enantiomer. So if I orientate it so that it's a mirror image, so then those are mirror images of each other, right? The green reflects to green, the red reflects to red, the white reflects to white. And then the blue reflects to blue. And so then this would match. So if this matches the molecule on the left, then this matches the molecule on my right. Okay. So let's, first of all, then let's just look at a few examples of molecules with chiral carbons and see if you can identify the chiral carbons in the molecules. So what do you got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 molecules. Let's circle all of the chiral carbons, if any, in these molecules. So some are easy to identify, some are not. So in this first molecule, for example, so you have to find an atom that has 4 different things attached. If it has 2 of the same things, it is not chiral. So this carbon, for example, has 3 hydrogens, it is not chiral. This carbon has an OH, a hydrogen, and so going to the left, you run into a carbon, and going to the right, you run into a carbon. So that doesn't matter that those 2 atoms are the same, you have to consider the entire pathway. So if you go to the left, you go to a carbon, and then that carbon goes to 3 hydrogens. If you go to a right, you go to a carbon, and that carbon has 2 hydrogens and another carbon attached. So the point is that this is a different pathway than this, so that's 4 different things. So that carbon is chiral. So that's a chiral carbon. And then this carbon is not chiral because it's got 2 hydrogens on it, and this carbon is not chiral because it's got 3 hydrogens on it. If it's got 2 of the same things, cannot be chiral. Must have 4 different things. Okay, so the next molecule, so that carbon is chiral because it's got a hydrogen. That's one thing. So the next 3 things is carbon, carbon, and that's a carbon, right? But you don't stop, you consider the entire pathway. So this carbon is attached to 3 hydrogens. This carbon is attached to 2 hydrogens. And this carbon is attached to basically 2 carbons because it's got a carbon-carbon double bond and 1 hydrogen, and those are different. Right, so that carbon is chiral. And that's the only chiral carbon in that molecule because all of the other carbons have at least 2 of the same things. So this carbon has 2 hydrogens, that's got 2 hydrogens, that's got 2 hydrogens, that's got 3 hydrogens. This carbon only has 3 things attached, right? It's got a carbon-carbon double bond, so it's got that carbon attached, it's got that carbon attached, and it's got that hydrogen attached. Can't have 3 things, it's got to have 4 things to be chiral. So that's not a chiral carbon, and that's not a chiral carbon because it's only got 3 things attached. So basically any carbon that's a double bond can't be chiral because it doesn't have 4 things attached. Okay, so for these molecules, that carbon's not chiral, it's got 2 hydrogens. That carbon's not chiral, it's got 3 hydrogens. That carbon is chiral. It's got a hydrogen, it's got an oxygen, and it's got a CH2, and it's got a CH3 attached, 4 different things. Okay, this molecule does not have any chiral carbons, right? That carbon's got 3 hydrogens, that's got 2, that's got 3 hydrogens, that's got 2, so those can't be chiral. This carbon in the middle has a fluorine and a hydrogen, that's 2 different things. But this is the same as this. It's got 2 alpha groups attached, so it doesn't have 4 different things, so no chiral carbons in this molecule. So if we took the same molecule and we attached a chlorine here instead, then now this way is different than this way. So now that carbon is chiral because it's got a fluorine and a hydrogen, and going towards the right, it's got an ethyl group, and going towards the left, it's got an ethyl group that's got a chlorine on it. That's different, so that's 4 different things. Is that the only chiral carbon in that molecule? And the answer is no, that carbon is also chiral. So this has 2 chiral carbons. This carbon in purple is chiral because it's got a chlorine attached. It's got a hydrogen, it's just not shown, right? There's a hydrogen atom there. And it's got a methyl group attached, and it's got all of this attached. So that carbon's got 4 different things attached. Okay, these 3 molecules, how many chiral carbons in each one? Well, that's not chiral, it's got 3 hydrogens, that's got 2 hydrogens, that's got 3 hydrogens, that's not chiral, but that is. Because it's got a methyl, it's got an ethyl, it's got an oxygen, and it's got a hydrogen on it. That's just not shown. So that's got 4 different things. That can't be chiral because it's got a double bond, so it's only got 3 things attached, right? 2 oxygens and a carbon attached to it. That carbon is chiral, right? It's got the hydrogen, it's got the NH2, it's got all of this attached, and it's got all of that attached. So that's 4 different things. And what about this carbon? It's a little tricky. That is not a chiral carbon, right? Even though I use dash wedges to show 3 dimensions, that may throw you off, but that carbon does not have 4 things attached, right? Because that is a CH3 and that is a CH3. It's got 2 of the same things attached, so it cannot be chiral. Okay, this molecule, that's a chiral carbon and that's a chiral carbon. So it does not matter that these 2 carbons have the same 4 things attached. What matters is that each carbon individually has 4 different things attached. Right? This top carbon, for example, has a hydrogen, a chlorine, and then what's important to recognize is going this way around the ring is different than going from that carbon this way around the ring. Right, because if you go towards the bottom, you go to a carbon with a hydrogen and a chlorine, and if you go towards the top, you go to a CH2. Right, so if you follow the purple pathway, you run into a CH2, and if you follow the green pathway, you run into a CH that's got a chlorine. That's different. So 4 different things, and the same would be true for the bottom carbon. If we go to the next molecule, that carbon is chiral, and that carbon is chiral. Right, because this carbon's got a hydrogen and a chlorine, and then going this way around the ring is different than going this way. Right, because going to the left, you go to CH2, you go CH2, 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 and CH with a Cl. Going towards the right, you go to CH2 and then a CH with a Cl. So that's different pathways. Okay, if we take this molecule, it has none. Right, because if we take this carbon, for example, it's got a chlorine and a hydrogen. That's 2 things. But if you go this way around the ring, that's the same as going this way. Because you go to CH2, CH2, CH chlorine. If you go around the top, around the bottom, you go to CH2, CH2, CH chlorine. Same pathway. So no chiral carbons there. So just to illustrate the importance of chiral centers, this molecule, for example, how many chiral carbons does it have? 1. That's a chiral carbon. This one cannot be because it's got 2 hydrogens. And none of these in this ring can be chiral because each of those has a double bond, so each of those only have 3 things attached. So this is an important molecule. This molecule is called phenyl. Alanine, ever heard of it before? Some of you may have heard of it. It's an amino acid. And of course, amino acids are important biologically. It's what proteins are made out of. So you find chirality all over the place in biological chemistry. This will be another example. This is C6H12O6, pretty important molecule, type of molecule in biological chemistry, right? That's a sugar. How many chiral carbons does it have? Well, that's a chiral carbon, that's a chiral carbon, that's a chiral carbon, that's a chiral carbon, and that's a chiral carbon. So that has 5 chiral carbons in it, right? Each of those carbons has 4 different things attached. Does not matter that they may have the same 4 things attached. They don't. None of them have the same 4 things attached. Each of those carbons is unique. But each of them has 4 different things attached. So that's one more example from biological chemistry. This is a pretty important molecule in biological chemistry as well. That molecule is cholesterol. So you can pause the video for a minute if you want and see if you can circle all of the chiral carbons. It's got a bunch. So let me circle all the chiral carbons for you. So first of all, that is not chiral because that carbon has 2 methyl groups. That is a chiral carbon, and that is a chiral carbon, and that is a chiral carbon. So is that, that, and that. So it's got 1, 2, 3, 4, 5, 6, 7, 8 chiral carbons. So anyway, most biological molecules are very complex molecules, and they have a lot of them amino acids, DNA, RNA, lipids, sugars, chiral carbons. And so we'll talk a lot more about that in this chapter. Okay, so molecules that are mirror images of each other, but are not superimposable on each other. So that would be right like those. Those are mirror images, but not superimposable on each other. These 2 molecules are said to be enantiomers of each other. So enantiomers are non-superimposable mirror images of each other, and so this will be an example. Okay, so what are the similarities and differences in enantiomers? So the similarities are a lot. Enantiomers have the same physical properties, same melting point, same boiling point, same solubility in any solvent, which means they're very difficult to separate. So if you had these 2 molecules and you wanted to separate them, that is not easy to do. You can't do distillation because they have the same boiling point. You can't do crystallization because they have exactly the same solubility. There are ways to separate them, and we'll talk about those later. And they also have the same chemical reactivity so long as they're reacting in a non-chiral environment. So pretty much they're very similar in almost all aspects except for basically 2. So 2 ways that enantiomers differ from each other. One is what's called their optical activity, which we'll talk about next. And one is their chemical reactivity in a chiral environment, such as a biological system, which is chiral because you have proteins, RNA, DNA, lipids, sugars that are all chiral. So chiral molecules react differently in a chiral environment, but in a non-chiral environment, they react exactly the same. Okay. So as importance of the significance of it, so thalidomide, this molecule is called thalidomide. So it's an important example of the significance of chirality and why it matters so much. So this is a molecule that back in the 1950s and 60s, it's a pharmaceutical agent that was administered to pregnant women to help with sleep and to help with morning sickness. And at the time, scientists didn't understand chirality very much. And so if you have a molecule with 1 chiral center, then there's 2 possible stereoisomers, right? They're enantiomers of each other. Well, it turns out one of these enantiomers has useful physiological properties, like helping with sleep and morning sickness, and the other stereoisomer, this one, turns out it had teratogenic activity. So if you know what a teratogen is, it's something that causes birth defects. So the women, this is more of a problem in Europe than the United States, but women who took this medication, it was originally administered in its as a 50-50 mixture of the two stereoisomers. And those women who took that medication ended up having babies that had severe birth defects. So this was not understood at the time, but now, of course, it is understood. So anytime that new pharmaceutical agents are synthesized that have chiral carbons in them, then you must separate the two molecules and you must study both of them, their physiological activities, to make sure the one that is useful, make sure that the other, its stereoisomer, is either useful also or is not toxic. If it's toxic, then obviously you can't administer it. So in which case you would have to find a way to separate the two molecules so you only administer as a medicine the one that is useful. Okay, so one difference between enantiomers is their biological activity. This is a classic example of differences in biological activity, and the only difference is the stereochemical arrangement around that one chiral carbon, but huge effect physiologically. And the only other difference in enantiomers is what's known as optical activity. So what is optical activity? So it's the ability of the chiral substance to rotate the plane of polarized light. And you measure the substance's optical activity using an instrument called a polarimeter. So this is basically how a polarimeter works. You have a light source. Usually it's a sodium filament, like in some light bulbs. If you heat sodium up to a high enough temperature, it will give off light. And it will give off light in all dimensions. So this just illustrates two dimensions, for example. Either propagating like that or propagating like that. But it does it in 360 degrees in all dimensions. And if you pass that light through what's called a polarizing filter, then it will filter out so you have light propagating in all dimensions, right? But if you pass it through a polarizing filter, then the light that comes out is only propagating in one dimension. So we'll call it the dimension of the piece of paper, for example. So that's what's called plane polarized light. I'll just call it PPL. So if you pass that light through a chiral substance, then what happens is the chiral substance, so it goes into the chiral substance, and then the chiral substance rotates the plane of the polarized light. And then what you have at the end is basically just a scope that you can use to measure the degree of rotation of the plane polarized light. So a plane polarized light is not rotated, then the sample is said to be not optically active. If plane polarized light is rotated, then the sample is chiral, and it's said to be optically active. So enantiomers rotate plane polarized light by the same magnitude, but in opposite directions of each other. So if we take these two molecules, for example, so they both have one chiral carbon. So the methyl group and the alpha group is in the same spot, but if you notice the hydrogen in the OH has been flipped from being on the solid wedge and dash wedge, or vice versa. So if you take a chiral carbon and you just switch two groups, that changes the stereo center from one enantiomer to the other. So these two molecules are enantiomers of each other. So one of them rotates plane polarized light counterclockwise, so that's what the negative means, by 13.5 degrees, and the other one rotates plane polarized light clockwise. That's what the positive means by 13.5 degrees. So same magnitude, 13.5, but opposite directions. So one of them would rotate plane polarized light this way, and then one would rotate plane polarized light that way, opposite directions of each other. So this molecule is called L2-butanol, or -2-butanol, or R2-butanol. So L and minus means, so L minus means levorotatory. So that just means it rotates plane polarized light counterclockwise. And this one's called D2-butanol, or +2-butanol, or S2-butanol. And the D or the plus just tells you the direction that it rotates plane polarized light. D or plus means dextrorotatory. It means it rotates plane polarized light clockwise. And we'll talk about what R and S means in the next lecture. So this is the way optical activity is defined. So alpha in brackets means optical activity. So it's equal to the measured optical activity divided by the concentration of the solution. So in this experiment, what's the concentration of that sample? And L is the path length. So L would be what is the length of this cell. because obviously as the cell is longer, then the plane polarized light is in contact with the chiral substance more, and it's going to rotate plane polarized light more. And it should be concentration dependent, because the more sample in that chamber, the more concentrated it is, then the more the light is going to interact with the molecules and rotate plane polarized light more. So we're not going to do any calculations with optical activity in this class. You just should know how it's defined. So for our plus 2-butanol, for example, its optical activity would be reported like this. The 27 means the temperature, because optical activity is temperature dependent. D means that's the sodium D line. So that's the light source. And then it tells you how much it rotates plane polarized light. And then S2-butanol then, of course, is exactly opposite. So this is basically a constant for a molecule. So if you made R2-butanol to the exact same concentration, then it should always have an optical activity of negative 13.5. So if you made a solution and it's not 13.5, you would know the sample is impure. Okay, so some other definitions to know. So optical light purity. So if something is said to be optically pure, then that means there's 100% of one stereoisomer. Optical purity is the percent of one enantiomer minus the percent of the other enantiomer. So if you had a solution that contained 75% of L2-butanol and 25%, yeah, L is minus, right, and 25% of plus or D2-butanol, then the solution would be 75 minus 25 would be 50% optically pure. So if you had a solution that was a 50-50 mixture of enantiomers, so a 50% mixture of the plus and minus stereoisomers, then that solution is said to be racemic. So another term that you should know. So then its optical purity would be 0%. Okay, so hopefully you can identify chiral carbons in molecules now and understand what optical activity is. And so that will be the end of that lecture.